EGU session and the co-chaired the Climate Informatics 2020 conference. The talk today is about accelerated climate science with machine learning, climate model emulation. The floor is yours.
Fantastic. Thank you very much, Luca. And thank you for the kind introduction. It's great to be speaking to you all. I've tried to keep the tried to bear in mind you're not, climate scientists, and I've tried to keep it fairly high level and just give an overview of the kind of work we're doing in using machine learning in our climate work. But if you do have any questions, particularly clarifications during the talk, I'm happy to be interrupted. But otherwise, there should be plenty of time for discussion at the end. It's possible I'll get interrupted this end. My son's currently off school with COVID, so apologies if that happens. But hopefully we'll have a smooth talk. Just at the off, I wanted to address a seemingly subtle, but actually I think relatively important distinction between machine learning for weather and machine learning for climate science. And I think sometimes these get conflated, and particularly people from the AI community maybe won't necessarily appreciate the distinction. I wrote this perspective last year after the workshop we held in Oxford, because I think there was some, I don't know, I just felt that there was this confusion. So I tried to articulate why it's different and why that's important. So if we think of the weather, and I'm going to do this in pretty abstract terms now. I don't have any pictures of umbrellas and the rain and stuff, sorry. But if we imagine the weather as or the state of the Earth atmosphere system at a particular time as capital Y here. In weather prediction, we're looking to project that state forward in time. And the difficulty lies in the fact that the atmosphere is a chaotic system, and for very small perturbations in your initial conditions, you will get a large diversity in your future states at some small increment forward in time. Maybe it's a few hours, and if you're doing nowcasting, maybe it's a few days in medium range weather forecasting. But nevertheless, you're looking to, as best as you can, capture this underlying diversity in future states of the system at a small future time. And really, to improve your weather models, you're trying to reduce this spread as much as possible, and or reduce the time it takes to generate ensembles that sample from this underlying distribution. And so there's been work from a number of groups exploring using machine learning to do that. Now, in the climate setting, two subtle things changed when I did that slide transition. Observant among you will have noticed that this is now wide bar. This is now an average state that we're primarily interested in trying to predict. And the small delta t is now a capital delta T, denoting the fact we're now trying to look tens, if not hundreds of years into the future. And the main effect of that is that we no longer really care about the way that the system got to that state. We actually care a lot more about how the average state responds to an external forcing. So this is denoted X here. And this could be due to changes in incoming solar radiation, natural solar cycles, or perhaps more classically, the effect of added greenhouse gases from burning fossil fuels. And what we want to know is how the system as a whole, the average system, responds to this external forcing. And so what we're primarily interested in is this change in the average atmospheric state of the system due to a forcing. And so this means that rather than an initial condition problem, climate can be cast as a boundary condition problem. And that means that we don't necessarily have to emulate the full dynamical evolution of the system in order to emulate the climate response to an external forcing. So I'm not going to be talking today about any of the cool stuff that people at DeepMind or NVIDIA have been doing in trying to project the atmospheric state forward in time. What I'm really looking to do is emulate this climatic response to a change in the boundary conditions. And one of those forcings which we're interested in is the aerosol forcing. Now, this isn't kind of aerosol as in spray can aerosol. This is aerosol particles, which are typically nanometers to a few microns in size that are suspended in the atmosphere. And they can be naturally occurring. They can be dust or sea salt. But the particular aerosol we're interested in are man-made. So these are more often than not sulfate particles that are emitted when you burn dirty fossil fuels, such as coal and heavy oil. And we're responsible for a lot of the, I don't know if some of you might be as old as me, but we remember the discussions on acid rain in the kind of 70s and 80s. It's caused by these sulfate particles forming sulfuric acid in clouds. And so the same sort of processes actually cause a change in the top of atmosphere radiative fluxes. So these aerosol reflect a bit of sunlight back to space, but they also change cloud properties in such a way that the clouds become slightly brighter. And so by changing the brightness of the clouds, we change this top of atmosphere radiative balance, and we impart a forcing on the climate. We change the balance of equilibrium of the climate state. And that's about as much climate science as I'm going to do today. But I just wanted to kind of give you a feel for what, you know, the particular questions that I'm interested in trying to answer are. And the reason it's important is that it affects our ability to predict future temperature change. So there's a fair amount going on in this plot, but I'll just break it down. So this is historical temperatures plotted in black here from kind of 1980 up to present day. And this is temperature change since the pre-industrial, so since I think it's an 1850 baseline. And what I've taken in the background here, this heat map, is actually the full plausible set of climate projections from the recent IPCC report, shaded by the aerosol forcing that those ensemble members exhibit. So this ERF-AER is just the technical term for the aerosol forcing. And it could be quite large and negative, around -1.5, or it could be relatively small. And what you notice is that where the ensemble members have a large negative forcing, what happens is that those members exhibit a larger than average warming under this particular scenario into the future. And conversely, if the aerosol forcing is cool, that means that the climate is likely to warm less in the future. Now, this is a pretty wide range of uncertainty. This is like a 90% confidence, if I remember correctly. But nevertheless, it spans these two crucial Paris Agreement kind of markers at 1.5 and 2 degrees. So even if we could get the politicians to agree on this particular socioeconomic pathway, we as a climate scientist wouldn't be able to say with a great deal of confidence whether or not this would actually be kind of Paris compatible. What we might be able to do, I'd like to be able to do, is predict aerosol forcing with greater precision. Maybe if we knew it to within 1/10 of a watt per meter squared, these are the units of forcing. And if that were the case, and it happened to be that it was on the low end of our predictions, then we would be able to confidently predict that we would be able to stay within 1.5 degrees. Whereas if we were to find that it was at the upper end, we might be able to say only with 50% confidence that it's within 2 degrees, but at least we'll have a better handle for what's going on. And so these are the kind of things that motivate me in trying to better represent these aerosol processes and the climate models and explore some of these uncertainties. So where do these come from? Why do we end up with these uncertainties? I mean, the physics of climate change is pretty well understood. We have a good idea on the general response. But I think just to take a step back and think about where these climate models come from, and this is where there is actually a fair amount of overlap with weather forecasting, is the way that we model the atmosphere. So this is a finite element discretization of the atmosphere in order to model the fluid dynamical evolution of the atmosphere. And that we can do pretty well because we have pretty good tools now for being able to solve these kind of equations, even for the chaotic system of the atmosphere. The difficulty is that there are many processes. The difficulty is that to be computationally viable, these grid cells can be at best kind of 1 kilometer if we want to do things just for a few days into the future. But if we want to do climate simulations for hundreds of years, these are typically of order 100 kilometers each grid cell across. So they're pretty coarse. And so any process, anything that affects the evolution of the atmosphere or the radiative balance that happens on a scale less than 100 kilometers, which is all of the kind of stuff down here, and pretty much all the stuff I've described so far in terms of aerosol and clouds, has to be parametrized. We have to come up with a simplified representation, often a functional form that kind of captures the average response of these processes over the scale of interest. And this is about as hard as it sounds. It's very difficult to find a representation of these systems that will work in any of these grid cells all of the time and produce a robust representation. And so that's where a lot of the difficulties lie, and that's where a lot of these uncertainties stem from. Nevertheless, we have a number of these models and increasing complexity, and different modeling centers around the world put a lot of time and effort and energy in developing these and then running different scenarios forward in time. So this is kind of taking another step out from the previous plot I showed you on forcing. So this is now considering multiple different scenarios. So what happens is there will be a group of scientists and economists and various different social scientists who will say, well, who will agree on a set of plausible scenarios. And they'll say, okay, well, maybe if everything goes swimmingly and we convince China and the US and Russia and Saudi Arabia to stop drilling oil and we transition rapidly to a green economy, then maybe we end up on this green curve. If there's some reluctance or there's some regional disputes or hesitancy, we end up on the yellow one. And if everyone just says sod it, we just we go hell for leather and just burn everything we find, then we end up on the red curve. And so these are supposed to somehow represent this kind of socio-political uncertainty, right? The fact that we don't know where as a society we're headed. And this is generating these kind of plots. So this is this, I don't think the number of dollars that went into the simulations that underpin these kind of curves. So each of these lines will have been simulated by around 15 of these climate models. I've plotted them from 2020 here, but in order to get these simulations, you have to have run historical, you have to spin up the ocean. I haven't even talked about the ocean, but it takes about 500 years of simulation just to get the ocean equilibrated. So there's a lot of investment goes into these. And what was my point? Oh, okay. So, but there's still this uncertainty, right? So one way I quite like of plotting or thinking about these different uncertainties is this representation after a nice Hawkins paper in 2009. But basically, you take those error bars from the last plot, and you just take the fractional uncertainty from each of them and plot them up like this, and measure the contribution to that uncertainty from 3 different sources. So there's this model uncertainty, which I've been talking about. So the fact that we can't perfectly represent these processes, we're stuck with, imperfect discretizations of the system. And that's this blue curve here. This is just for global mean temperature. These look quite different for other quantities, but if we just stick with global mean temperature for now, it's relatively simple. There's scenario uncertainty, which is the fact that we don't know where we're going to end up, right? We could be on this burn everything curve, or we could be on a big green curve. And so that's this kind of green patch. And there's also internal variability or variance. So it's not really weather, because weather is very short term. It's more internal variations in the ocean system, which has a larger, longer timescale variance, but is nevertheless less important for climate. But as you can see from this, it tapers off towards the end of the century. If we wanted to do decadal predictions, then it is, it's important to know whether there's an ENSO coming up, for example. But anyway, the key point here is that particularly for middle of the century kind of projections, model uncertainty is a very large contribution to that, if not the dominant term, to our uncertainty and being able to estimate what the change in temperature will be. As we go towards the end of the century, and you can kind of tell from that previous plot, scenario uncertainty becomes key. So I'm gonna drill down actually into each of these and explore how we can use climate model emulation to both reduce this uncertainty and explore and better quantify these two uncertainties. So first of all, I was going to say, I'm going to start with exploring this model uncertainty and how we use climate model emulation for calibration. But maybe I just pause there just quickly in case there are any questions about the framing or any aspects of the kind of climate science motivation. No? Okay, good. All right, fine. So yeah, so if we want to try and reduce this uncertainty in terms of what our models are doing, then the first thing we need to do is to be able to better calibrate the various parameters that we have in there. So I refer to this kind of exploring parametric uncertainty because there are a number of you can think of, if we think of our climate model as a super complex function f, right? And it has a number of input forces x, so these things like the solar forcing, the greenhouse gas, the aerosol forcing. And it has a number of parameters theta, and these could be these physical parameters that go into our parameterizations. And it generates a whole load of output y, and this is generally high dimensional, and there's an awful lot of it. But if we just say that, well, our climate model is just a fancy way of mapping these emissions of greenhouse gases and these parameters to some outputs that we're interested in, like temperature change or precipitation change. What we'd like to be able to do to better kind of inform our model or calibrate our model is, assuming we know X, which we do more or less over the historical period, and observations of the system, then we'd like to be able to answer the question of which parameters the inverse, right? So which parameters are most likely to make our climate model output something that looks like observations? Or conversely, if we put observations into this inverse, what parameters would come out? This isn't always a well-posed question, and so we can frame it probabilistically and ask what the probability of a set of parameters theta is given our observations. And so this is just the obligatory Bayes theorem. The difficulty here is obviously the likelihood function, maybe not obviously, this likelihood is intractable. It's high dimensional, and we don't know it. We just don't have access to it in this setting. So we use an approach known as likelihood-free inference, which some of you may have come across, and in particular, approximate Bayesian computation or projection sampling. And this is just for a non-ML person, this is great because it's super simple. We basically just draw samples from our prior, we draw samples of parameters from our prior. We put them forward through our forward model to determine our outputs, and we accept that set of parameters if for some distance metric, so some similarity between our observations and our output is less than our tolerance. And it can be shown that, well, you can see trivially that if you make your tolerance really big, then you are just drawing observations from your prior. But it can be shown that as the tolerance goes towards zero, then we generate theta from this posterior. Now, in practice, you have to do this tens or hundreds of thousands of times. And so this forward step, this forward model is too computationally expensive. And so we use a surrogate model or an emulator to approximate that. Now, this distance metric is a key component of that. And for this work, we use the concept of an implausibility metric. So I've cited Vernon here, but I think it goes back further as well. It's essentially just the standardized Cartesian distance between the observations and the emulator output for a given set of theta. standardized by the prediction uncertainty, so our emulator uncertainty, an estimate of our observational uncertainty, where it's available, but also an estimate of the structural uncertainty. So the fact that however good we make these parameters, the model might just not be able to fit it because it's a finite discretization of the climate system. And then assuming this is unimodal, which is actually a pretty good assumption, we can use the 3 sigma rule to rule out parameter combinations at 95% confidence. So we just we use I as our distance metric, and we set epsilon to be 3, and we can reject any theta which are not compatible with our observations. So here's a concrete example. So here I've just taken a really simple ensemble where we've explored just 3 parameters. So we're looking at a particular type of aerosol. This is an absorbing type of aerosol known as black carbon. So it's the kind of soot, the black exhaust you see coming out of really dirty trucks or trains when they're pulling out of the station. And the 3 parameters we wanted to explore were just the emissions of this aerosol, so how much is put into the atmosphere, the removal of it, so how efficiently the atmosphere rains out this aerosol, so how long it lasts for in the atmosphere, and then thirdly, the absorptivity, so how absorbing it is, and that's this imaginary part of the refractive index, IRI. So those are two of the parameter dimensions, and then we have an output variable here, which is just some measure of the total amount of absorption of this in the atmosphere. And we sample this 3-dimensional space using Latin hypercube sampling. We just take 30 or 40 different samples, and we get different outputs from our climate model. So we run each of these dots is 1 year of simulation from our climate model, which took, I remember now, it's about 4 or 5 hours on 256 nodes each. So not nothing, but not crazy expensive either. And then the active emulation is really just to regress this space. So we use Gaussian process regression because it deals well with fairly low amounts of data and gives us a well-calibrated uncertainties as well. And once we have that, then we can do this rejection sampling. Then we can do this step of just looping through and calculating the implausibility and accepting or rejecting various different combinations of these parameters. So red dots here are parameter combinations that have been compared to observations and rejected, and green dots are accepted. And as we do this over time, we build up our posterior distribution, and we see, particularly in this lower left-hand corner, there's a slice through this space that is compatible with the observations. There's no one kind of number that's right, but rather we could have a low amount of this black carbon emitted, but it's very absorbing, or we could have more of it emitted and it's not very absorbing, right? You end up with this kind of duality, if you like. And you can see that on this, actually, that if you took a slice through this plane, there's a region where you can find compatible model simulations. Now, this approach is fairly old hat. People have been doing this since late 90s in various guises. There's, I think, a fair amount of room for innovation in the way we apply it in the community, in the climate community, and I'm keen to kind of engage more with the ML and the stats community to kind of update the way we do this. There's some kind of interesting, I think, aspects to our particular problem in that we have access to very high dimensional outputs. So the Y that we use as a constraint can be very large. That makes this implausibility quite difficult, right? Because you have the curse of dimensionality. That means these distances, these Cartesian distances, become very small. But I've developed a tool to try and bring the climate community along, if you like, and ease their way into using this, because although it's fairly old hat, it's still relatively new in the climate community. And it just kind of provides a way of making it easy for people to take their model data, combine it with observations, train an emulator, and do this kind of inference or calibration step. So this is this ESEm tool we've developed. And the one kind of novel or nice thing about it, that rather than just kind of interface, is that this rejection sampling all happens in TensorFlow. So you can do the, you build an emulator using GPFlow or something, and then the rejection sampling happens on the GPU. So you can sample and reject hundreds of thousands of these outputs a second. And they needn't be one-dimensional either. They can be, despite the difficulties I just mentioned, they can in principle be high-dimensional. So this is a map of this aerosol absorption quantity. And you see, you know, there are regions in the world, particularly in northern India and in eastern China, where it's quite large, and other regions where it's quite small. But the GP gas process does a really good job of predicting this on held out data. And we've also developed actually a CNN. We're interested to see whether spatial covariances would be, you know, provide us anything different over the GP. It's not quite as skillful in this case because there's quite limited training data. So this really is just still the 30-odd training samples that we had before. So it's quite challenging to train a neural network over that. But these are the kind of things we're exploring. And I'll maybe come back to other kind of steps forward we're looking to take at the end. But nevertheless, we can scale this up in terms of the parameters quite considerably. So people have been looking at kind of 30, 40, 50 parameter ensembles, exploring different aspects of these aerosol processes in the models. And we've had good success in constraining various aspects of the climate system. I won't go into details here, but that works quite well. I think I just need to answer the door. So excuse me just for one moment.
Sure, no problem.
Okay, sorry about that. But actually, that's a good point to end that section. So that's kind of where we're at in terms of trying to squeeze this model uncertainty. The other aspect I mentioned was being able to, we can't constrain this scenario uncertainty. It's inherently unknowable. But one thing that would be useful for policymakers is to be able to explore that scenario uncertainty, explore these various possible future climates without having to run a whole ensemble of climate models to find out what the answer would be. So I have a colleague actually who was at COP26 in Edinburgh, and they were the kind of climate science community was slightly caught unawares by the proposal from, I think it's from the US, they had a fairly ambitious methane proposal, cutting methane emissions, and we didn't really know. We hadn't crunched the numbers on what the implications of those were for future temperature change, and so, you know, people were using quite simple emulators just to explore the global mean temperature response. But it would be amazing to be able to do that with a full emulator of maps of temperature change and precipitation. And so that's what we've been exploring with ClimateBench. So this was inspired by WeatherBench, but as I mentioned, you know, the setup is quite different, and what we're interested in is quite different. So we introduced this new ClimateBench. So I just submitted the paper just before Christmas, and that's available on ESSOAR if you're interested. But the basic principle is to, as I say, build on these simple emulators which take emissions of greenhouse gases such as CO2 and methane and some of these aerosol properties. And they produce these profiles of global mean temperature change. And these actually are key, as I say, for policy applications. But what we'd like to be able to do is predict maps of temperature change and maps of precipitation change and other quantities of interest. And again, this can be framed as a regression problem, right? We have training data from our climate models. And so we set this up as a hackathon challenge during a workshop in September. And the task was to take these emissions profiles. These are actually maps of aerosol, but global mean values of carbon dioxide and methane, and predict this dotted line, right? So you're given these red lines, the climate model output and the inputs for these other scenarios, but this particular scenario is held back. And the task is to estimate or predict temperature, change in global temperature, spatially, diurnal temperature range as well, precipitation and extreme precipitation. And the training data that was available, we tried to kind of span this input space so that the models were interpolating rather than extrapolating. I'm not quite sure how clear this plot is, but these are global mean values of sulfur dioxide, methane, black carbon, and CO2. And what I'm trying to show is that each of these colors represents a set of training data from one of these climate models that we used to train the emulators. And they come from various different types of experiment in the database that we had. So some of them were these scenarios that I mentioned, so forward in time, these different scenarios, which are in green. And these tend to end up with quite high values of CO2. These explore this kind of corner of this space. We also have the historical simulations. So these go back from present day back to 1750. And so these tend to explore quite low values. And then there's some idealized simulations, which are used primarily to understand the physical response to the climate system. And these tend to hug the borders because they'll hold one of the things constant while varying the other. So you kind of get into the edges of the distribution. And the hope was that by combining these various different sources of experiment, we create a training data set. Oh, I had all this on the slide. Yeah, I won't go through all of that. Yeah, that spans the input space. It's not perfect because some of these are correlated, right? It wasn't an ensemble that we designed to sample this space maximally efficiently. It was kind of an ensemble of an opportunistic ensemble from the CMIP6 archive, but nevertheless seemed to be pretty useful. And so 8 teams participated, and then we ranked them based on the RMSE across these various variables for the second half of the 21st century. And it was quite nice, actually. So 3 of the best models were different models. We had a random forest, a Gaussian process, and an LSTM CNN. And they all did really well, actually. I was surprised. So these numbers don't necessarily mean a huge amount, but for context, I put a different climate model. So different climate model ran the same simulations, and this is the RMSE between that one and the one that we used for training, right? So this gives some indication of the spread in what these state-of-the-art climate models have, and you can see that these emulators are all much smaller in their diversity from the target model than the intermodel diversity. We can see that from maps of these as well. So this is maps of the temperature change predicted by the neural network and the Gaussian process. And this is the target output data from the particular climate model that we were using, nor ESEm2. And you can see they both capture the key structures here, right? There's a land-sea contrast. There's polar amplification, which is a well-known phenomena whereby the poles warm more than the mean. And there's also the North Atlantic warming hole, which is, again, a well-understood phenomena. Diurnal temperature range. Again, you're really squinting to try and tell the differences. If you look carefully, this region just to the north of Nepal, the model, both the machine learning models underpredict the change, interestingly. So it's something we're looking to dig into. But for precipitation, both in the kind of mean precipitation as well as extreme precipitation, the models do a really good job of capturing that. They tend to slightly under-predict the extreme precipitation, but again, that's something that I think with a bit more time and a bit more effort could be rectified. One of the key considerations in developing a climate model is the physicality of it and conservation of key quantities such as energy and water and mass, because we're running these things out into the future and we don't have very good opportunities for validation and verification. Right? We want to be able to trust them, and so a lot of the trust in our climate projections hinges on the physics. And so one key aspect, this goes back to an important paper from Miles Allen here in Oxford at the start of the century, that shows that the global mean precipitation change is strongly controlled by the global mean temperature change, and this is just a reformulation of energy conservation. And what's quite nice is that the emulators all broadly respect that. This GP at the tail here seems to be a little bit too shallow, but they all broadly follow what the climate model does. And I think this is really cool, but it's not entirely unexpected, because we train it on temperature change, we train it on precipitation change. So I would hope that it would get the slope, but nevertheless it's it's an indication that it's doing something sensible. But there is still room for improvement. Just finally, and relatively quickly, because it's not my area of expertise, but there is also an opportunity here for sampling this internal variability, the variance. So one of the models, the GP model, we tweaked that slightly, and because it predicts, because you get a robust estimate of the variance of the posterior of the GP, we realized that actually that's telling you something about the internal variability of the system. It's telling you about the fact that it doesn't know exactly what the temperature change is going to be at 2100 because of the noise of the climate system. And so these three kind of pastel color lines are three samples from the underlying kind of climate model, the true model in this setting. And the Gaussian process mean prediction is in the red line, and the shading is the one sigma estimate of the variance of the standard deviation. Sorry, and it's probably over predicting the variance slightly. It looks like, but nevertheless, I think again, given the timescales involved, I think it's a nice indication of the potential of this kind of approach. So, in summary, hopefully I've kind of demonstrated some of the techniques that we're using from machine learning to create Earth system model emulators for both parameter estimation and constraining uncertainty. We can use similar emulators for exploring scenario uncertainty with higher fidelity outputs and robust uncertainties. And I think both aspects offer data and science-rich opportunities for machine learning to tackle some of these really big questions. There's lots of outstanding challenges, and I welcome interacting with the ML community to try and understand how we can figure out when the emulators stray out of the training distribution, more explicitly encoding some of these physical laws and symmetries, and yeah, many others, which I hope we can touch on in the discussions. Thank you very much.
Thanks a lot. It was a very interesting talk. Are there any questions? Yeah. So I see, okay, a lot of questions. Yeah, Dana, please.
I think those are the clapping hands, not the raising.
Oh, okay. Okay. Okay, there are no questions then?
Yes, not.
Okay, then I have a couple of them. In my work, I guess also Matteo's work, we are working on ML for agriculture, and there are a lot of similar problems. Like there are a lot of emulators that are used to simulate crop growth, for example.
Okay.
and you don't want to throw them away using, for example, ML to fit for like, let's say, real world data.
Yeah.
And so, for example, surrogate modeling, it's something that we are exploring. And that was, I wanted to ask if there are like, so in your problem where you used, you just use this model to basically check what is the most plausible. You had one of the parameters, you held it out so that to see which one was more plausible. If you have an idea of how to come up with like meaningful priors, because you know your surrogate model can learn a very precise model where you don't need it. Yeah. And in that case, it kind of maybe it's not a problem in kind of models, but it could happen. And then your whole loss function, let's say it's basically the loss function is given by an area of the parameters that are not interesting, and then your model is not very useful, but you think it is. So I don't know if you address that problem.
Yeah, no, you're absolutely right. And this, you know, I don't think there's any magic bullet for that. I think you have to work closely with the scientists to understand what that space looks like. I was a little bit loose with my terminology here. So there's a distinction between calibrating climate models, so finding the best set of parameters that you know fits our observational state, versus uncertainty quantification, whereby actually, which is more typical for this this ABC, this kind of rejection sampling, where you're not really saying these are the best parameters, these are just ones that we can't rule out with the observations we're given. Sure. And it absolutely makes a big difference what your priors are, where you end up in that space. And I think that makes some people uncomfortable, particularly, you know, domain scientists, right? I still think, and maybe, I don't know, maybe in ML too, but, you know, this Bayesian way of thinking is a bit uncomfortable. The fact that the answer depends on your point of view, right? That's how it can be framed. But we just have to be explicit about what priors we're using and why. So if we just want so there's a group I work with in Leeds, and they're I'm trying to think of the right way of putting it. Their belief, right, is that they should start from a uniform prior, because that will better, because they don't want to assert any kind of knowledge on the system before determining what the uncertainties are. And I would assert that that's too, by doing that, they're making a statement about their belief of it, right? That even if they say we'll have uniform priors, then they're making the positive statement that they know nothing about where any of these parameters should be. And I think they're actually being too kind of conservative, if you like, in then what their posterior estimates of the uncertainty really are. And I think if you use informed priors, then you get potentially a better representation, depending obviously where you know how you inform those priors. But you know, it's a really good question. There's no magic bullet, and I think we just need to be explicit about how we treat that. But yeah, you're absolutely right.
Thanks. Yeah, I mean, in our case, we are trying to, yeah, indeed, as you said, collaborate with people that have knowledge about these systems and try to have an answer from them, basically.
Yeah, but it's really hard, right? If you ask a scientist, what's the full range that this parameter could possibly be, and they might say, well, it's a float. You know, it's minus infinity to infinity, right? And okay, but you have to get somewhere to work with, or sometimes they go the other way. Sometimes they say, oh, we really know what the uncertainty is, and maybe that's even less helpful.
Alex, we have another question, or is a clapping hand again?
No, I think there's a hand up.
No, yeah, this is a hand up. Thanks again. Really interesting talk. I just had, my background is not so great on this, and I just had a question. There was a slide in the aerosol forcing section where you displayed all of the, like essentially the massive area of uncertainty about how aerosols could push us down or upward. If you could go back to that, could you go back to that slide, because there's a question about exactly. I was curious if I had missed it, or if why have the colors flipped sides in the historical situation? What happened here?
Yeah, good question, good spot. So so this particular forcing, it depends which direction you take as up for your radiative balance, but the negative sign here, if you notice, these are all negative forcings, and this is because aerosol impart a cooling. If you introduce this sulfate aerosol into the system, they reflect some sunlight back to space and they impart a cooling, so they reduce the amount of sunlight warming the earth. And if nothing else was going on, you'd get a small drop in temperature. Now, what happens is that up to around the year 2010 or so, I guess, maybe a little bit before, in this setup, aerosol emissions were increasing. So the amount of aerosol emissions from burning fossil fuels, primarily in China at this time of year, but before that it was in Europe and North America. And so if you had a weaker aerosol forcing in that scenario, you get less, right? But then when the aerosol emissions kind of turn over around 2010, and in this scenario now going down past the present day, and so then a weak aerosol forcing is leading to cooling. But it's really, yeah, good observation. Okay, so yeah, so just to make sure I understand it, that's the essentially kind of a display of the amount or of how that large amount of aerosol is impacting the atmosphere, and as we go into the future, it'll actually have reverse effects had in the past because of the potential warming effects it can have versus its cooling effects. Exactly. You're unmasking the warming that we should have had almost. Yeah. Oh, excellent. Okay, I see. Thank you very much. No worries.
If nobody else has a question, may I ask? I didn't raise my hand, but
please.
Yeah. So I was curious about the, what's it called, the implausibility metric that you say you use for calibration.
Yeah.
Because maybe I missed it, but like you mentioned, like the curse of dimensionality, like this is very high dimensional object, and like why, I guess it's a very high dimensional object, and therefore you like get very small distances. What are we talking about? Like what is the kind of observation you're calibrating against? Because in the example that you showed later, in the end, we had a 2-dimensional, I mean, maybe this is just because we can just visualize 3-dimensional, but we had 2-dimensional calibration problem with one objective, right? With this, I kind of, I forgot the exact quantity, but.
So here, for example, or.
I think when you were showing the fit of the Gaussian process model, that was two inputs and one output. I think we were calibrating against this AAOD.
Okay. So in kind of more operational, if you like, or more kind of state-of-the-art applications, the dimensionality of theta is around 20 or 30. The dimensionality of y really could be tens or hundreds of thousands, if not millions, if we had the tools to do it. They're not all IID, right? There are sometimes strong covariances. But we have an awful lot of data that we could potentially use. So, this one map of annual mean AAOD is around 80,000 points. As I say, there's strong correlation. There's not a lot of information in many of these. we typically do PCA, and we'll keep like the top 10 because that's what gives us a reasonable handle on most of the variants. But we're throwing away a lot of information because we don't have a better way of informing this this implausibility. And any ideas or suggestions you have on how to improve that would be greatly received.
I mean, unfortunately not. Yeah, but I was curious also if there is, because I imagine Y being like a long array of measurements, like if there is like a sensible way of prioritizing some against the others, because I guess you're more interested in calibrating certain things, or if sometimes you treat it as a multi-objective optimization where like you cannot, well, I mean, okay, now you're talking about, I think I'm still thinking about the calibration as an optimization process, not as an uncertainty quantification problem, as you were mentioning before. But when like you can, like, well, how do you prioritize like getting better at predicting certain quantities, like having parameters that predict better certain quantities than other, and here it's all aggregated in one scalar. But yeah, so
I mean, another approach. So yeah, in practice we use dimensionality reduction, we use PCAs or so, and they're not ideal, but it gives you some way of doing it. The other way that people do this is not to do the dimensionality reduction here, but take a high dimensional I and then deal with that one way or another. You could say if you have say 5% of my I are really large, but the rest are small, then I'll keep it, right? Or you can come up with arbitrary ways of dealing with it, but you come up with you make some argument about how you might expect some of these to be quite close and some of them further away.
Yeah, okay, thanks.
Yeah, no worries.
And then, I mean, I guess I was also curious about, like, instead of part that you mentioned toward the end, but I guess you pointed out then in the final slide that this could be like a future direction when you basically, I think you were showing this like connection between precipitation and temperature change, and you were showing that basically like kind of the fact that the prediction models were coherent with what physics would suggest. It was shown as a sanity check of like, oh, the prediction models are making something sensible, but could we use this to make the prediction models better? I mean, could we use it as a constraint so that like we use physics and the knowledge we have about the system to inject prior knowledge? Exactly.
Yeah. No, I'm curious again, how we might do that. I guess, we could frame it as a multi-objective. If your neural network predicts both precipitation and temperature, then you could put in a kind of hard constraint such that the sum of both have to have this relationship. It's an interesting one. We'll have to, I think about how best to do that.
Yeah, sure. I mean, sorry, I didn't mean to interrupt.
No, carry on, please.
No, I mean, I meant more, it was just like, mine wasn't really a question. I think it sounds like an open problem. And it was, I mean, it's like, it's more like the question was very open. Like, what's your ideas? Or like, has anybody tried anything on that? But it seems this is very recent. And it's like, you're scratching the surface and there's a lot to be explored.
So it is, yes, it is very new and there's lots of ways of going at it. And I think, I know people are keen to try kind of physically informed neural networks and things like that. But one thing I'm keen to start on is the fact that we have these simple emulators that they're referred to as, and these really just solve a set of coupled ODEs that describe the temperature response to changing CO2 and greenhouse gases. And these are pretty simple. You can write them down. There's like 6 coupled equations or something. working with a student here to embed or construct a GP over temperature such that the global mean temperature is drawn from the solution of the ODE. And that's something which there's been a bit of work on in the literature, and I think could be really promising. It doesn't necessarily help for some of these other fields, but at least, you know, it's a way of encoding some of that physicality.
Nice, thanks.
Are there other questions? I don't know. Actually, regarding still this ClimateBench, so the input would be all this, just this 4 time series, and then you try to output because, like, I mean, the output is spatially, it has a spatial structure, right? So is the input also as a spatial dimension, or is just this time series?
Yeah, good question. So these two greenhouse gases are well mixed. So once they're emitted in the atmosphere, it doesn't really matter where they are. But the aerosol only stays in the atmosphere for a few days, and so it does matter where it's emitted. So we provide maps of these two,
I see.
and these two are just scalar quantities. Some of the models treat each time point independently, so that it's just a straight regression between you know, 2 scalars and 2 maps to these 4 maps. The LSTM model takes the full time series and learns the lagged response as well.
And so the scenario basically has to not only imagine the mean, but also for this SO2, also the spatial distribution of, okay.
Yeah.
So you imagine which countries are going to pollute in that direction.
Yeah, absolutely. Yeah, exactly.
Okay. Yeah.
Which is harder to predict, as you can imagine.
Yeah, that's what I was thinking about. And how is it done? The train and test for the split for the benchmark.
This kind of evaluation scenario was held back for the kind of competition to rank competitions, and then the models were free to do their test train split as they wanted. And it's, you know, in some respects it's maybe an easy scenario, right? Because it's right in the middle. It's middle of the road. If we had a scenario that did something a bit different, it'd be interesting to see, you know, how the models really performed. But then in that setting, there's no reason we couldn't take the climate model and actually do some experiments in the corner, right in the corners here, and provide a more, you know, bespoke, if you like, ensemble. So there's definitely room for exploring that.
Cool. Thanks.
But it's all on GitHub, so if you're interested to have a go at it, then you know, check it out and go.
So is it like a recurrent I don't know, like challenge or something, or is there a leaderboard? I haven't
quite decided yet. I mean, so there's a leaderboard up on the GitHub, and I'll happily add people if they, you know, if they publish a better model.
Okay, cool.
See how it develops.
Cool. Other questions? Then I guess we can conclude here. Thanks a lot again, Duncan, for the nice talk, and I'll see you everybody in 2 weeks for another talk. I guess it's going to be about biodiversity monitoring, and see you. Have a good one.
Fantastic. Nice to meet you all.
Thank you very much.
Thanks a lot. Thank you.
Bye.